Now come the corresponding symmetry relationships. So once we have derived these results, then we can write down the following. For example, supposing you want to look at property number 11. Okay, real part of x of n is given by 1/2 of x of n plus x conjugate of n, correct? And all we need to do is write down the corresponding relationships that we have. This will have a relationship which is given by x of k. This we know has got a corresponding a DFT relationship which is given by x conjugate of minus k modulo n. Okay, and therefore what we have is the following relationship: x of k, x conjugate of minus k is what we have, but minus k is interpreted as with respect to modulo n. So what we have here on the right hand side is 1/2 the corresponding relationship for the real part of x of n. The DFT relationship is given by 1/2 of x of k plus x conjugate of minus k, but minus k must be interpreted modulo n. Okay, but at the end of the day, this is minus k representation. So this can be viewed as the even part of x of k. Okay, so basically what we are showing is that the real part of x of n has got a mapping onto the even part of k. To get the even part, you would have to time reverse the signal, but the time reversal has to be interpreted modulo n, and that's what we have. Okay, so we can verify this is a result that has been verified. So number 12, I would like you to write down and verify exactly the same way that we have done. I would like you to verify. Let's look at number 13. Property number 13. Okay, x even part of n. Okay, this is given by 1/2 of x of n plus, you have to time reverse the sequence, conjugate and time reverse. The time reversal has to be interpreted modulo n. Okay, so this is the corresponding relationship. So what are the corresponding DFTs? In this case, the DFT, this case will be x of k. In this case, it is x conjugate of k, and therefore we get the relationship that x EP of n, the even part of x of n, has got a DFT relationship that is given by 1/2 of x of k plus x conjugate of k. Okay, when you add x of k with its conjugate, what you get, and divide by 2, what we get is this is equal to the real part of x of k. Okay, so that is what we have just now verified. Same way, please verify property number 14. Okay, verify property number 14. It's not difficult at all. Okay, now finally come the what are some unique properties when x of n is real. Okay, we have already shown some of these results, but what is important is when x of n is real, then here are the important results. X of n real, x of n real valued, this implies x of n is equal to x conjugate of n. Okay, what are the corresponding DFTs? This is x of k and this is equal to x conjugate of minus k modulo n. This is what we have already written down. Okay, so when you have two quantities which are related by a conjugation sign, you can relate the real parts, you can relate the imaginary parts. So here are the two corresponding results from here. Okay, the first one says if I compare the real part of the left hand side, it is real part of x of k will be equal to the real part on the right hand side, which will be the real part of x conjugate of minus k interpreted modulo n. Okay, and correspondingly we can get a second relationship from here, which is given by comparing the imaginary parts. The imaginary part of x of k, when you take the conjugate, it will be equal to the negative, right? The imaginary part becomes, so this will be equal to a minus sign times the imaginary part of x conjugate of minus k modulo n. Okay, so given that the real part is an even function, we say that it is an even function. The real part is the even function. The imaginary part is an odd function. Okay, just one more step and then we get the result that we are interested in. And the magnitude of x of k, okay, this will be equal to the real part of x of k plus the real part squared and imaginary part of x of k. Okay, so now when you look at and raised to the power half, square root. Now if you are looking at this is a product of two even functions, real part into real part. This is even function. Imaginary part is an odd function, but this is equal to odd into odd, which is given which will become even. Okay, so what we have done is x of k is square root of real part squared, imaginary part squared, and therefore we can write down, because it's an even function, is equal to x of when you look at the modulus, the modulus of the DFT coefficients. Now when I look at the minus k modulo n, I will see that k is the modulus of x of k will be the same as modulus of x of minus k, where minus k is interpreted modulo n. Okay, so basically this is so the magnitude of the DFT coefficients is even. The magnitude of the DFT coefficients, which is modulus of x of k equal to 0 through n minus 1, this is an even function of k. Okay, by the same token, if you look at the argument of x of k, it will be tan inverse. This will be tan inverse of the imaginary part of x of k divided by the real part of x of k. So what you have here is an odd function. This is an even function. So therefore the argument turns out to be an odd function. Okay, so the argument turns out to be as an odd function. The magnitude is an even function, argument is an odd function. Now, is that surprising? Not at all. Why? Because x of k is one period of x tilde of k, and x tilde of k are samples of the DTFT, x e of j omega. And what do we know as a property of the DTFT? The magnitude is an even function. The argument is an odd function. So given that we have sampled it at a symmetric points, that for every k there is a minus k also present, then we find that the argument, the magnitude of the DFT coefficients is an even function. The argument of the DFT coefficients So this is in some sense like a sampling of the magnitude response and the phase response. So of the DFT coefficients is an odd function of k. And there are examples in the book that show this particular result, and you can look at Oppenheim and Schaefer example number 3, where you can look at the particular sequence, look at the DFS coefficients, and then see that the magnitude response has got a even relationship, and then the phase response has got a odd relationship. And again, whatever is there for the DFS will carry forward when you look at it in the context of the DFT. Okay, so this is a completion of the properties that we are interested in. So we have completed a discussion of the symmetry properties, and for the special cases where x of n is real, we have also shown that the magnitude will be even function, the argument will be an odd function. So this is an important set of results. I hope you will be able to verify it and use it as and when these results are required. Now we will look at some important aspects where we will introduce the notions of the application of the properties that we have derived, and then get some important results. So let us summarize the properties that we have obtained. Okay, the important properties are the aspects of duality. Okay, how do you time reverse a signal? For a periodic signal, you have to interpret it correctly for when you do time reversal of the sequence in the context of the DFT. We looked at the multiplication of the DFT coefficients producing circular convolution in time, multiplication in the time domain producing a circular convolution in the DFT. Similarly, we obtained all of the properties that we have derived, and this is an important set of results that we have obtained. Now let's look at a couple of examples, because always the richness of any theory or result that we develop is in being able to identify and apply the results in a example.